But we can also use eigenvalues and our eigendecomposition. We can follow the same general idea or the same general procedure. If we take the determinant of our eigendecomposition for this A matrix, well, it's just the determinant of Q times the determinant of lambda times the determinant of Q inverse. If you'll recall, the Q matrix is just made up of our eigenvectors, so they will also be orthogonal or orthonormal by definition. So the determinant of these two matrices will also be positive or negative 1, and since one is just the inverse of the other, they will also have the same sign as well. So we'll get either a double positive or a double negative, meaning that the sign will just cancel itself out. We'll be left with something positive either way. And so we get that the determinant of our A matrix is really just the determinant of our lambda matrix, which again is a square diagonal matrix with our eigenvalues this time running along the diagonal. And so, because of that, the determinant of lambda is just the product of all of our eigenvalues. But this is where we run into some problems, and this is why a lot of people don't like working with eigenvalues compared to singular values, is because eigenvalues can be complex, and that obviously makes things much more computationally intensive, meaning from a numerical standpoint, this is definitely not the route to go unless you are already computing eigenvalues for some reason. But what we can do is, if we do have a complex product here, we can just take the real part of that complex number, and that will be our determinant. Let's test that out in the next block of code. So in this first block of code, I am computing the eigenvalues and the eigenvectors using the numpy lineage eig function. And the first thing that I want to test is I want to test to see whether or not the determinant of Q and the determinant of Q inverse are actually positive or negative 1. Then I'm going to take the product of all of our eigenvalues, and we'll see what we end up getting from that. From running this cell, the terminal output shows us that the determinant of Q and Q inverse are in fact not positive or negative 1, which means our theory is kind of off if we think about this. But if we look at the product of our eigenvalues and we look at just the real part and stack that up against with what we got previously using the numpy lineage determinant function, you can see that they're in really good agreement with one another, and we get the minus sign that we expected from before. So it does kind of hold up or work at the end, but the determinant of Q and Q inverse is not positive or negative 1. However, if we work with a positive definite matrix, it will guarantee that we have strictly real eigenvalues. And so to do that, I'm going to compute A transpose by A in this next code block and do the same thing all over again. And we can see from the terminal output that the determinant of Q and the determinant of Q inverse, if we have strictly real eigenvalues, is in fact positive or negative 1. In this case, it's positive 1. They're both positive. And so everything just works out exactly as we would expect. Obviously, this is a different value because this is the determinant of A transpose A now. But I just wanted to show you that to kind of emphasize that computing determinants with eigenvalues is not as straightforward. And again, we have to do complex mathematics, which is much more computationally intensive than we otherwise should have to do to compute determinants.